All right, guys, welcome to lesson 2. We're going to continue talking about these net change formulas that we've been learning about. Today we're just going to kind of work on analyzing them a little bit more. Last time was just the basic idea of what it is and interpreting it. This time we're going to do some stuff with it, like find the intervals where they increase or decrease, and finding the absolute extrema, average rates, instantaneous rates, and then interpreting all that stuff in the context of a word problem. So let's go ahead and take a look at our first example. Once again, you guys are going to be needing your calculators today, so make sure you have those handy. So example 1, we have a tide removing sand from a beach at a rate modeled by the function r that we see here. So that's how quickly sand is being removed from the beach, and this should be a t here, so let me fix that real quick. There we go. Where at any given time, if you plug in a t here, that will tell you how fast the sand is being removed from the beach, and that is going to be measured in cubic yards per hour. So t is measured in hours, and the amount of sand is measured in cubic yards, and so the rate here is showing us how quickly sand is being removed in cubic yards per hour. A pumping station adds sand to the beach at a rate modeled by the function s. So now, whereas the tide is removing sand, a pumping station is adding sand. Okay, so we have a rate in and a rate out here, right? It says both r and s are measured in cubic yards per hour, as I've already mentioned, and t is measured in hours, and it applies from 0 to 6. So we're only going from 0 hour to hour 6. And at time 0, which is the beginning, the beach contains 2,500 cubic yards of sand. All right, so here's what we're going to be doing in example 1. We're going to start by writing a function that we're going to call y of x that gives the amount of sand on the beach at time x. So that's the first thing we're going to do. So we're just going to turn this into a function. After that, we're going to find the intervals for which the function is increasing and decreasing. So without any further ado, let's go ahead and get started here. So the first part is actually just a review from yesterday. We know that in order to find the amount of sand, we just say, okay, y of x, the final amount of sand, is equal to the starting amount plus the net change from 0 to x. And net change can be found by taking your rate in and subtracting from that your rate out, like so. So there's my function that gives the amount of sand on the beach at any time x. All right, so now we're going to really get into the meat of the point of this example here, because that was just a review, but we need that to do this process. The real question we're trying to get to here is we want to find the intervals where the amount of sand on the beach is increasing and also where it's decreasing. All right. Well, since y represents the amount of sand on the beach, basically what I want to know is I want to know when is y increasing and when is y decreasing. So when is y increasing and then we also want to know when is y decreasing. Now, as you guys know, a function is increasing anytime its derivative is positive. So the answer to that would be y is increasing when y prime is greater than 0. And y is decreasing anytime that y prime is less than 0. So what we're going to want to do here is we're going to start by finding the derivative of y. So let's do that. So my function down there, y of x, I'm going to take the derivative of that. Now when you take the derivative, the constant's going to go away, right? And when you take the derivative of an integral, well, that's the second fundamental theorem of calculus, right? We drop the integral and we drop in the x. And so we end up with s of x minus r of x. Okay, so there's my derivative. And as you guys know, we really don't need to have the plus 0 there, so we can kind of just get rid of that. Let me erase it for a moment here. So all we really need is the y prime is equal to s of x minus r of x. All right, continuing onwards now. We want to know when is y increasing and when is y decreasing. In other words, I want to know when is y prime greater than 0 and when is y prime less than 0. So let's go ahead and begin with the first question there. When is y prime greater than 0? Since y increases when y prime is greater than 0, we can say that y is increasing anytime that s of x minus r of x is greater than 0, because that's my derivative. So this equation here and this one here, they're the same thing. I just wrote what y prime equals in the second case. So anytime y prime is greater than 0, y is increasing. So that means anytime s of x minus r of x is greater than 0, y is increasing. Now I'm going to go ahead and add r of x to this other side over here. So that means then that anytime s of x is greater than r of x, y is increasing. And that makes a lot of sense if you actually think about what these things mean. Do you remember what s means and what r means? S tells us how fast sand is being added to the beach. R tells us how fast sand is being removed from the beach. So basically what this is saying is that anytime you're adding sand to the beach at a rate that's faster than the rate at which you're taking it out, well then obviously your overall function would be increasing. That makes total sense, does it not? So there's that. Now how do we find where s of x is greater than r of x? Well, what we're going to do is we're going to look at a graph of our two functions. And anytime s of x is above r of x, then that's where s of x is greater than x. So in other words, s is above r of x. Okay? So we're going to graph it using our graphing calculators. So let's go ahead and pull out our graphing calculators and put those equations in, and let's graph them and find out where the s function is above the r function. So of course the first thing you want to do is you want to put your functions in. So I've put in the r function, the rate at which it's being removed, under y1, and I put s function, which is the rate at which it's being added, under y2. Now once again, you've got to remember that. You need to take a moment to write down a note or something somewhere that s is equal to y2 in your calculator and r is equal to y1. You don't want to get those mixed up, otherwise you're going to be getting wrong answers. So, all right, so there's that. Notice I put parentheses around my denominator here for my s function. That's important that you do that, otherwise you'll get the wrong answer whenever you try to graph it. All right, well, let's go ahead and we're going to push graph now. We may have to adjust our window screen a little bit. Let's see. I know I'll probably have to adjust mine because I've been messing around with it and I know that I changed the screen a whole lot. So this isn't going to look like yours. So bear with me while we wait for this thing to mellow out a bit. Now you guys might not have to do this at the moment, but it is very important that you guys, and you'll see later on today with other examples, it's very important that you're able to adjust your window because sometimes the amount of the graph you want to see isn't immediately available. So one way to get to a nice normal screen, just so you guys know, is to push the button that says zoom. And then there's a few different options here and you can experiment with them. But the one I'm going to pick right now is number 6, which is standard, which just means 10 by 10. So I'm going to go ahead and click that. Let's take a look there. Now, that might be what you guys are looking at right now. But just to kind of show you other things that we could do here, as you guys can see, my height is good because my curves are not going off. It's not like it's going above the place where I can actually view anything, so that's okay. I'm happy there. But so I'm not going to change the y values. I like the height. But notice the time value only goes from 0 to 6. So, and also I've got a lot of empty space down here that I don't care about. So I'm going to adjust my windows here. This is not horribly necessary for this problem, but there will be some where it's pretty important to know how to do this. So first of all, I'm going to put 0 for x because we're starting at 0 and we're ending at 6. So I'm going to change my x's from 0 to 6. I got there by pushing window in case you missed that. And then I'm going to go to my y values. Negative 10 was a little bit too low in case you guys don't remember. So I'm going to go ahead and change it to like maybe like negative 6. And my max, I was okay with the height. I don't think I want to mess with that. I liked the height. So I'm going to leave my y max the same. And I'm going to regraph this now. And that way you just kind of get a little bit of a prettier picture of the place you care about. Making it stop at 6, by the way, is kind of helpful because then you don't accidentally analyze more of the graph than you need to. But that's how you can adjust it. Now, we have our two functions graphed here. Now, remember, what we were trying to do is I wanted to find out when is s of x greater than r of x. And as you guys remember, my s of x was y2, and my r of x was y1. So I want to know when is the y2 function higher or above the r function, because anytime the s graph is above the r graph, well, that's an indicator that it is greater than. Okay, so what we're going to do is we're going to push the button here that says trace. Now, as soon as you push that, you're going to see a cursor blinking. And that cursor means that whatever function's up here in the top corner, that's the function you're on right now. So right now, I'm on the r function. All right, now over here we can scroll this. If you just push the arrow, it will trace that line that you're on. And notice that as you do that, just as a side note, it tells you the x and y value for those points you trace. But anyway, as I get over here, you can see that the r function seems to be staying above. Now it's possible that they're crossing right here because we can't really tell by looking. Now, I'm going to show you something right now that I'm not too worried about you mastering at the moment, but it's a cool little thing you can do. So you can zoom in on this. You could do it by adjusting your window, but there's another way. You can just push zoom, and then I like to use the Z box option, number 1. And what you do is you take your cursor and you put it in a spot, you click enter, and then you can click and drag a box around the spot you want to get a better view of, and then push enter again, and it will zoom in on that spot. I wanted to know if they're actually going to cross, and actually, as you guys can see, they don't. And so what that means then is that r function actually stays above the s function over there. So let me go back to my window and change it, though, because after you do that, your window goes to something else. So do 0, 6, and negative 6 and 10. All right, so back to the original graph. So as we can see here, the r function here stays on top of the s function the entire time until we get right about here at this point. At this point, the s function, which I'll trace in green here, is actually going to be above the r function at that point. And that's what we were looking for. We were looking for that point in time when the s function is greater than the r function, and that's whenever the s line is above the r line. Okay, so what we need to do is we need to find that point. Now you could push trace and get a pretty close estimate. You know, you could push trace and get really close. I don't want you guys to do this, though, because it doesn't give you a very good answer, but, you know, because right about here, right? So it looks like maybe we'd say about 5.23, but there's a better way. And the problem is if you don't get this right in the AP exam, they won't give you credit for it. You need to be correct up to the thousandths place. And so this way is not the best way to find where they cross. here's a better way to find where they cross. You're going to push second, you're going to push trace or calc, and then you're going to click intersect, which is 5. And then once your cursor's on top of that point that you're trying to look for where they cross, all you're going to do is you're going to push enter 3 times. 1, 2, 3. And that will give you a perfect estimate as far as the calculator's ability to do so. And we end up with 5.118. So they cross at 5.118. Okay? So from 5.118 up to the end, which we stopped at 6, right? That is when the S function is above the R function. So let's go back to our original problem here. We were looking for where is Y increasing and where is it decreasing? Now, Y is increasing anytime S is greater than R. And we found that that happened on the interval from 5.118 up to 6. Why am I stopping at 6? Because that's where our story problem stops. It doesn't go beyond 6. Okay? And we saw that for the rest of the interval, R was above S. That means that R is greater than S. Y is going to be decreasing anytime the rate out is less than the rate in. And so R was constantly above S from the very beginning of the story problem up to that point where they switched places. Okay? Now it's possible for, when you're doing these problems to have two functions, and you might have 2 spots where they cross. And when they have 2 spots, then you're going to have 2 separate intervals where it's increasing or 2 separate intervals where it's decreasing. You have to look for both spots where they cross. But the point is this. So let's review. How do you know when the function is increasing? It's increasing when the rate in is greater than the rate out. It's decreasing when the rate out is greater than the rate in. How do you do that? You graph them and you find the place where they intersect, and that helps you know where it goes from one function being above to one function being below. So I'm going to let you guys try a problem like this now. Let's move on to homework problems 1A and 1B here. So pause the video and try homework problem 1A and 1B, and when you unpause it, we'll share the solutions. So here's our integral function that tells us how much water would be in the bucket at any given time. Now, let's go and take a look at our graph. So this is what my graph looks like. I adjusted my window so that my x values just go from 0 to 10. That was random just because we didn't have a limit this time on the number of x's. But for my y values, I left the y at -6. It didn't really matter. But for my y max, I went up to 30 because the initial amount was 20, so I wanted to go a little bit higher than that. So that's my graph, and that's what it looks like there. And so we would have needed to find this place here where they cross, right? So doing that, the one that looks like this, which I'll trace in green right now, that is the rate in, and the other one is the rate out, okay? And so the question, when is A increasing? Anytime the rate in, which is F, is greater than the rate out. And that would be on this interval right here. So from 0 to that place where they cross. After that, they switch places and the rate out function is greater. And so where do those two lines cross? Let's take a look. At 1.667. So on the answer number 2 is that A is increasing on the interval from 0 to 1.667, and A is decreasing on the interval, in other words, when G is greater than F, is after that point. So from 1.667, And it didn't give us a stopping point, so we'll just put infinity there. Although in real life, of course, the story problem would end as soon as water stops being poured in there. But anyway, there we have it. So those are the two answers for number 2. All right, let's go ahead and take a look at example 3 here. This one says the tide removes, well, it's actually the same problem we had earlier, so I won't read it again. It should look familiar. Let's go ahead and take a look at number 7. So it says let y represent the amount of sand on the beach. We already found that equation earlier, right? Let me refresh your mind as to what that is. All right, so there's that. We got that back in example 1 there. Now it says find the average rate of change of y of t on the interval from 0 to 10. So I want to know the average rate, which can be calculated by doing y of 10 minus y of 0 over 10 minus 0. And my calculator, once again, is going to come to the rescue here. All right, so let's go ahead and take a look at our calculator. So first of all, we want to go back and, of course, put those functions back to the ones we were working with before, right, the beach equations. Now, we're going to put a new equation in here, actually. I want to put the integral equation in that I just had written up on the board. And that integral equation, y of t, was 2,500 plus the integral. Now, this is pretty cool. You can put an integral in here. You're going to push math. You're going to push 9. And there's the integral. So we're going from 0, and it's a function, so we're not going to put a number here. We're going to put an x here. And then we're going to put y2 minus y1. Actually, yeah, y2 was in, y1 was out, right? So it's y2 minus y1. So I'm going to push vars. I'm going to get the y2 function in there. y2 minus y1 and dx. Now, I wouldn't encourage you to try to graph this, so don't push graph because it's too much processing power for the calculator to handle, and it takes forever, and sometimes your calculator just never gets to it, and you have to pull the batteries out to reset it. Not advisable. They just can't handle graphing those, it seems, a lot of the time. So don't push graph. What we're going to do is we're going to go to second quit, and we're just going to calculate the formula that I put up on the board earlier for the average rate of change. It was y of 10 minus y of 0 over 10 minus 0. Okay, so here we go. We're going to push vars, and my integral function was option 3. I just typed that in, so it's y3 was the integral function. So it's y10 minus y0 equals, now I'm going to do the top first and see how long that's taking my calculator to calculate. That's hard for it to work on those integral functions. It took a little while. So that's the top, but we also want to divide that by, we want to divide that entire answer by 10 minus 0. Now, just so you guys know, you could have typed the whole thing in all at once, but if you did, you would want to put parentheses around the y3 of 10 minus y3 of 0. Otherwise, your calculator will get confused. So you'd have to put parentheses around the entire top and parentheses around the entire bottom. But it doesn't matter. I just did the top separately and divided it by 10. But there's my answer. So that's the average rate of change on that interval. So my answer to number 1 then will be 1.740. Remember, we always round to the thousandth place. Now, we're going to, I want to interpret this even though it doesn't really ask us to do that, but your homework will have some questions like that, so I want you guys to be familiar with it. So what this means is that on average, this is an average rate of change, on average, the amount of sand on the beach is increasing. Now, how do I know it's increasing? Because my rate is positive. My average rate of change is positive. So on average, the amount of sand on the beach is increasing on the interval. You have to specify the interval because when you do an average rate, you'll get one answer for one interval, but a different answer for a different interval. So the average rate of change on the interval from 0 to 10 is on average increasing, and I forgot to put by how much, by 1.740. We want our units in there, and that would be cubic yards per, I think it was hour, I believe. So there's your final interpretation. It has all three parts, the units of the input, output, and the context. So that's the interpretation for that one. All right, let's go ahead and go back now and take a look at another one. So number 2, find y prime of 3 and interpret your results using the appropriate units. So basically I want to find the derivative of my net change integral function and plug in 3, and then we want to interpret our results. All right, so let me begin by interpreting the results. This is an instantaneous rate of change. Now contrast that with up here, we talked about an average rate of change. So when you find a derivative and plug a number in, that tells you an instantaneous rate of change. So the only difference in the interpretations between these two is that this one's going to say this at the exact moment of t equals 3, the instantaneous rate of change of the amount of sand on the beach is blah. Okay, so that's the only difference, is it's an instantaneous rate at a single point instead of an average rate over an interval. They're both rates, though, so this is a rate. But let's get to the calculator work. The calculator, once again, is going to do that. And you might be wondering, why are we using the calculator for all this stuff? We know how to find derivatives and stuff like that, right? Well, because on the AP exam, they'll give you equations that look like the ones we're working with, and they do that on purpose because they don't want you to do it by hand. If you tried to do these derivatives by hand, it would be a nightmare. So they really want you to know how to use the technology. So that's why we're doing it this way instead. But yes, technically, if you know how to find the derivatives of the functions, you can always do it by hand. But let's go ahead and do this. So now, as you guys remember, I put the integral function in here under y3, and that's the one I want to find the derivative of at 3. So I'm going to go back to my home screen here, and here's how you find a derivative. You're going to push math, and you're going to scroll down to option 8 where it says in derivative, and you're going to type in the information. So we're finding the derivative with respect to x, and I'm taking the derivative of the y3 function, and we're doing that at x equals 3. And once again, this takes a lot of processing power from our calculators to work with these integral functions. So as you guys can see the little bars moving up here, that's my calculator thinking, and it finally gave me an answer of negative 2.49. And so the answer to number 2 is that y prime of 3 equals negative 2.490. But what does that mean? We're going to interpret it now. This means that at t equals 3 hours, the amount of sand, which is given by y, is changing, because we're talking about a rate, is changing at a rate of negative 2.490 cubic yards per minute. Okay? Now, instead of saying changing, you could say it's decreasing. So another way to say this is you could say at t equals 3 hours, the amount of sand is decreasing at a rate of 2.490 cubic yards per minute. Was it minute? It was hours, wasn't it? All right. So, and like I said, I think they do prefer you to say whether it's increasing or decreasing instead of just saying changing. And notice that since I said it's decreasing, I didn't make it negative, because if you're saying it's decreasing, that means it is negative. If you say decreasing and you put a negative there, that's like a double negative, and that's actually incorrect. But there you go. So this is actually the better way to say it. So I'm going to erase this, and I'm going to encourage you guys to put that there instead. So at t equals 3 hours, the amount of sand is decreasing at a rate of 2.490 cubic yards per hour. You could even say it's decreasing at an instantaneous rate if you wanted to, but that's not entirely necessary. All right, so my last question is just to kind of show you something that has to do with units and interpretations here. So it says find r prime of 3 and interpret your results using the appropriate units. Well, here's r. Now here's what's funny about that. The units for r are cubic yards per hour. And I want to find the derivative of r, okay? Well, this is already a rate. So when you take the derivative of a rate, you get a rate of a rate, which is kind of like a second derivative. And as you guys might recall, when that happens, instead of cubic yards per hour, r prime is going to be cubic yards per hour, or you could say per hour squared, okay? Furthermore, it tells us how quickly this rate itself is changing. So the derivative of r tells us how fast r is changing. So, you know, the tide is removing the sand from the beach at a certain rate. R prime of 3 will tell us how fast that rate itself is changing. In other words, it's like an acceleration. So let's go ahead and see how to do that, and then I'll show you how to interpret it. All right, so first of all, you definitely need to remember what your R function is. My R function for me was y1, okay? So coming back to my screen here, we want to find R prime of 3. So that's the derivative, so I'm going to push math. I'm going to choose option 8. And I'm going to put x here, and I want to put r in this spot, which can be done by putting y1 in there. So vars y1. And we're doing this at 3. And there's my answer. Calculator didn't have a problem with that one because it's not an integral function. It's just a regular function. All right, so we have now our answer. R prime of 3 is equal to 0.158. And let's interpret that. This means that at t equals 3 hours, the rate at which sand is being removed from the beach or from the shore. Now, all of that is a sentence that captures this concept right here. That's R of t. R of t is the rate at which sand is being removed. So, at t equals 3, R of t, or the rate at which sand is being removed from the shore, is increasing or decreasing? It's increasing at a rate of 0.158, and we got to get our units right here, where R is measured in cubic yards per hour. R prime is going to be in cubic yards per hour squared. Okay, and so there it is. At t equals 3 hours, the rate at which sand is being removed from the shore is increasing at a rate of 0.158 cubic yards. So that means at the 3rd hour, the waves are actually removing sand from the beach at a faster and faster pace. It's like an acceleration, if you will. And so when you take the derivative of a rate, you get like an acceleration, right? It's an old concept that we talked about, but just doing it in these contexts of these rate in, rate out questions. So let's throw one of these at you guys and see how you do. And I just realized up here earlier it said example 3, but it's example 2. All right, so here's your guys. You guys are going to do homework problems 1C and 1D. All right, when you're all done, go ahead and check your answers and unpause the video, and I'll have them up here for you. All right, so here is the answer for part C here. This is the average rate of change, and then the interpretation you guys can see here. A prime of 2 equals 1, and you can see the interpretation here. And f prime of 2 is 2. That's kind of interesting. And that the interpretation is there. All right, moving on to our next bit and our last bit for the day. All right, let's read our story problem here. At a certain grocery store, customers remove bananas from the display table at a rate modeled by that. And yes, by the way, I do believe these are real formulas created by mathematicians who made the AP test. They actually calculated these things. I was told that these are legit scenarios. So somebody actually figured out how fast people are taking bananas from a display rack. That's interesting. Anyway, and employees add bananas to the display table at a rate modeled by this. Now both F and G are measured in pounds per hour, so we're talking about the weight of the bananas over time, which is measured in hours. And there are 20 pounds of bananas on display at t equals 3. Now, something important to notice is that our starting point this time is 3. It's not 0. That's different. There's a reason for that. I'm not going to go into it right now. It's not a big deal to us. But just know that our starting time is not 0. And so that is going to affect how we write our function for this, right? So let's go ahead and do it. I'm going to create a function here. I'm going to say, let's call it just f. No, we can't call it f because we already have f. Let's call it b for bananas. The number of bananas is equal to the starting amount of bananas. Now, what's the starting amount of bananas? It's 20 pounds, right? But remember, the starting amount doesn't happen at t equals 0. It happens at t equals 3. That's going to change something. Can you guys predict what that will change? Think about it for a second. It's going to change the fact that we don't put 0 right there. That's not our starting point. My starting point is 3. Okay, so that is a subtle little difference there. Now also notice I put g minus f. Why? Because g is how fast it's being added. F is how fast it's being removed. So there's my function. Now the question here is asking me to find the minimum and maximum. They mean the absolute minimum and maximum and on this interval here. So we need to do the candidates test. Our old friend, the candidates test. So we start at 3 and we're ending at 12. And we need to find those critical values. Now, critical values are anywhere where the derivative is undefined or equal to 0. So let's find our derivative. B prime is equal to what? Well, the 20 is going to go away. The integral is going to go away, and the x is going to drop inside. Second fundamental theorem of calculus. So b prime is equal to g of x minus f of x. Right? Now, is it ever going to be undefined? Well, probably not. First of all, we know that sine is never undefined, so that's okay. Sine is continuous everywhere. ln is continuous everywhere it doesn't equal 0 or less, and the inside could never have 0 or less in there, and so that we're good. There's no places where these functions will be undefined, so I'm going to ignore that. But I will say that we can find where it equals 0. Now, if g of x minus f of x equals 0, you guys know what that means? That means that g of x equals f of x. And you know what that means? That means where they cross. Anytime two functions are equal, that means that one's not greater than the other or less, in other words, above or below. If they're equal, they're right at the same spot. They're crossing each other, okay? So my critical values are going to happen where my rate out function crosses my rate in function. And once again, we're going to go to our calculator to find where they cross, okay? So let's go ahead and do that. So make sure you've typed them in correctly. 10 plus 0.8x sine of x cubed over 100, and 3 plus 2.4 ln of x squared plus 2x. All right, so there's my two functions. Now, we're looking for critical values. Critical values are where the derivative equals 0. And we found that if b prime equals 0, then that's where g of x equals f of x. In other words, where these two functions are equal, and on a graph, that's where they cross. So we're going to look for the places where they cross. So we're going to push graph, and we're going to look at our graph. And notice I've reset my calculator to be in a standard view here. I just, now, as you can see, this is not a very good window to look at. Now, I know that we're looking at a time interval from 3 to 12. So I want my x-axis to go from 3 to 12, but I don't mind leaving the 0. I think I'm going to leave 0 on here just for the heck of it, but we really only care about from 3 to 12. And then also, it's going off the chart. I can't see what's going on up here. I can't see where they're crossing. So I need to adjust my window again. So I'm going to go to Window. I'm going to set x minimum to be 0, and I want x max to be 12. I might even go a little bit past 12 just so I can see a little bit what happens after the 12 where they cross. Or I don't know, that's not where they cross, that's just where the story ends. And then the minimum, there was absolutely nothing below the x-axis, so I'm just going to go ahead and set the y minimum at 0. And I saw that my y max wasn't high enough. How many bananas were there to begin with? Wasn't there like, how many pounds were there to begin with? There were 20. So that's the starting amount. So I want to be higher than 20. Let's go ahead and make it 40. That way it starts at 20, and that gives us a little bit of wiggle room to increase if necessary. Let's go ahead and graph that and see if that gives us a better picture. So sometimes you just got to mess with it to find these sorts of things. All right, so I think I gave it too much height. Now you could leave it like this if you want to. I don't like this. I'm going to change the window. I want it to be shorter. I want it to only be like maybe this high. So if this is 40, 20 is probably like right about here. So I'll make it like 25. You don't have to. I just like my window to be a little bit more pleasant to look at. It gives me a clearer view of what I'm dealing with. So. And remember, we're looking for the places where they cross, and that's happening at quite a few spots here. So we're going to have a lot of critical values. All right, so they're crossing here, 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 and I'm not sure if this one counts or not because we don't want to go past 12, but we'll see. All right, so let's go ahead and find those points. Now we already know how to do that. So remember, I'll refresh your memory here, but you push trace. I'm sorry, you don't push trace, you push second, and then you push trace. And you're going to click the button that says intersect, number 5. You're going to put your cursor, you're going to move your cursor until you get to the place where they're crossing, and you're going to push enter 3 times. And there it is. Now I want to show you guys something really interesting here. I don't want to have to write this down, and also every time I write it down, I'm rounding it and I lose accuracy. I want to keep this number where they're crossing exactly as is. So I'm going to store this number on my calculator. This is a new skill I'm teaching you guys on the calculator. You ready? So first of all, you're going to push enter. It makes it look like it goes away, but it doesn't. And then you're going to push this button down here that says store. And that takes you to the home screen. And we're going to store this under a letter. I'm going to store it under letter A. So let's push alpha. And then right underneath of that, you guys see there's a little green A on the button above math. Put A and then you put enter. And now my calculator knows that A is that value where they cross. Let's go back to our graph and continue the process. Now let's do another one. Let's find this point where they're crossing. So once again, second, calc, intersect, scroll over to where they're crossing, enter 3 times. There's the next point, 8.826. But I'm not going to write it down, I'm going to store it. That's going to come in handy. So we're going to push enter, we're going to push store, and then we're going to push alpha, and now I want to store it under a new letter. Let's do B. That's the next button over there, B, and then enter. And now my calculator knows that B is that other value. It'll keep it for me in its memory. Let's go back to our graph. Why don't you guys try doing the other ones here? And when you unpause it, I will have had done all the other ones. Now, the only one we have to be careful with is this last one. If it's more than 12, we don't want to use it because remember, we're only going from 3 to 12. But pause the video here and see if you can find these other points of intersection, A, B, C, D, E, and maybe F. And when you unpause it, I'll show you my answers. All right, guys, so here's my A, B, C, D, and E values. So now let's refresh, remembering what we were doing. We had the story about bananas being removed and added. We have an integral function. We're trying to find the absolute min and absolute max. You put in your endpoints, which we have are 3 and 12. And then you find your critical values, which is where the derivative equals 0, which means that that's where the functions are equal and where they cross. And we just found all those places where they cross. So those places where they cross give us the critical values of the amounts of bananas. And you'll notice that I did not include the last point, which I was going to call F, because it was past 12. We would not include that one. And now our job is to find all of these values. I need to find b of 3. I need to find b of a. I need to find b of b. And by the way, it's okay for me to use these letters on my FRQ so long as I've defined them. I can just put the letter E instead of 11.477 so long as I've defined that 11.477 is in fact E. All right? And so now, I know this might seem like a terrible thing to have to go through here because there's so many of them, but actually our calculator is just going to do all of them, and it's as simple as just doing the same thing over and over again. So I'm going to do my B function with 3 A, B, C, D, E, and 12 plugged in, and I'm going to put all my answers in as I go. So let's do that, and that will show us which ones are min and max. All right, so now I'm going to go ahead and I'm going to type in the integral function that we were working with. So let's go down here. I believe that, let's see, the starting amount was 20 bananas, right? So we have 20 bananas plus the net change. So that's an integral, math 9. And our starting point was different, remember. It's not 0, it's 3 for this problem because our starting point was 3. And then we do our rate in and our rate out being subtracted from each other. The rate in is y2 on this problem, and the rate out was y1. Now remember, I don't want to graph that. That would be a nightmare. My calculator will never get it done. It takes forever. But I will go back to the home screen now. And remember, I've got all these values of my critical values stored under these letters, so that's really nice. All right, let's go ahead and start figuring out these things. So I stored B under the equation y of 3. So I'm going to do vars, y3 this time, and we're just going to start plugging these values. So the first one I'm going to plug in is 3. So let's do that, which we should already know the answer to that. It's 20, right? That's the starting amount of bananas at that time. So let's go ahead and write that number on there. 20 pounds of bananas for B of 3. All right, continuing the journey. Now, instead of bringing up y3 again, you can just push second and then entry, and it will bring back the same thing. This time you just have to scroll back on top of the 3, and we're going to put A in there. So you push alpha, A, enter. And it will plug in the value that we had stored for the A, and it will save us a little bit of time. So we're looking at 14.460. All right, let's repeat. So second entry, scroll back, let's put B there, alpha B, enter, and we're just going to keep doing that over and over again. So luckily, we have a calculator to do this for us so we don't got to keep doing it repeatedly. And this is a real AP question, by the way, you guys. All the FRQs that I usually give you are real FRQs from the past. So this is the kinds of questions you can expect to be seeing. I'm really trying to get you guys more and more used to those as we get closer and closer to the test date. I would encourage you guys to try to do this on your own. I'm just going to keep doing it, but see if you guys, if you want to pause the video and try to do these on your own, make sure you know how to do these keystrokes. That would be wise, because you're going to want to be able to do those things on your AP exam. Being able to store values is very important, not just because it saves time, but also because of accuracy. Because every time you have to stop and write something down and truncate it because it was too long, you're estimating it, you're rounding it, and that loses accuracy for you. And so you end up with a less accurate answer than originally. So when you store the value, though, it keeps it in there exactly as it was initially without any rounding. So it's good to know how to store. All right, and we'll be using that probably some more in this unit. All right, last one. we want to plug in the 12. And we've got, it's going to ponder for a long time on that one, 40. Well, it looks like it was just increasing the whole time. So I can see now that my maximum was here at B of 12, unless I did something wrong. And then my minimum actually was right here at B of A, that initial value of A. So there you go. That's how you find a minimum and maximum of a net change integral function. Very common. There's a whole section of those devoted to blue books. If you look at your blue book on the cover, there's things called rate in and rate out. And whether or not you have to find a min or a max is a very common question. So this is a great one to practice. So here's homework problem number 2. I want you guys to find the minimum and maximum of the amount of fish in the lake on the interval from 0 to 24. And for this problem, I give you a recommendation of a window view to adjust to. All right. When you unpause it, you'll see the solution. All right, guys. And so here's my answers. I have my equation representing the amount of fish. Of course, you know that we need to find the derivative of that, which would just be e of x minus L of x. And then when we set that equal to 0, that would indicate to us that e of x equals L of x. In other words, we're looking for the place where those two rate functions cross each other. And those are our critical values, a through d here. And the top and the bottom, of course, are the endpoints of the interval that we care about, which is a 24-hour period. All right. And after you plug those into your function, you get a minimum at the very beginning is 100, and the max is where the most is at the end of 422. So at 24 hours later, we start with a maximum number of fish. At the beginning of time, we started with 100 fish. And that's the end of the lesson.